Today, we want to look at the many forms of quadratic functions. We've got a new one for today, a third one. We've got a standard form, which we're familiar with. We've got the vertex form, which we're familiar with. And today I want to throw in the factored form, which is a little bit new. We want to look at what each of these forms tell us and how we can switch from one form to the other. How do we go from standard to vertex? How do we go from vertex to factored? How do we go from factored to standard, and so on? How do we get around the three forms? Let's first talk about what the three forms tell us. Actually, let's first do an application, and then we'll see the three forms. So here's an application of quadratic functions that is very popular. An object is thrown with an initial upward velocity of, I can't remember what I used, an initial upward velocity of 64 feet per second. From an initial height of 80 feet. So an object is thrown, say, from an 80-foot tower, thrown upward, and the vertical velocity is 64 feet. We only care about the velocity going up and down. We're not worried about how much of the velocity is going forward. We know that up and down, it's going 64 feet per second. Now we know what's going to happen if we throw an object upward from a tower 80 feet high. It's going to go up for a little while, and it's going to slow down as it goes up until it reaches its highest point, and then it's going to start falling towards the ground, and then later on smack into the ground. So using this information, we can write a function for the height of the function at a given time after it was thrown. The height of the function, or the height of the object, at, let's say, x seconds after being thrown is given by a quadratic function. So let's write the quadratic function. Let's say f of x is negative 16 x squared. Talk about where the negative 16 comes from in a minute, but the other two numbers are going to be, it's going to be very clear where they come from. Negative 16x squared plus 64x plus 80. So here is an equation that gives the height of the function at x seconds after being thrown. Now I should clarify, this is the height of the object in feet. It would be really weird with the initial velocity in feet per second and the initial height in feet to have this come out in meters or something like that. So it's the height of the object in feet at x seconds after being thrown. So it looks like it's easy to build the standard form of a quadratic function, of the height function, if we have the initial velocity and the initial height. So the 80 is where we get is the initial height in feet. So there's the 80, that's our initial height. The 64 is our initial upward velocity. And the negative 16 is half of the value of the acceleration due to gravity. There are reasons that we're only using half of it, but this is 1/2 of the acceleration due to gravity. Sometimes we call that g. G is negative 32 feet per second per second. So the way that gravity works, as long as we don't go too far from the Earth, and this is gravity on Earth, the way that gravity works is that the acceleration due to gravity is constant. So if something starts to fall, 1 second later, its velocity will lose 32 feet per second moving up. So if we just drop something from a high tower, so its initial velocity is 0, then 1 second later, its velocity will be 32 feet per second. 2 seconds later, its velocity will be 64 feet per second. 3 seconds later, its velocity will be 96 feet per second. Because gravity is changing the velocity of the object by 32 feet per second every second. And we call it negative because we're going to assign down to be the negative direction. Negative velocities are down, and positive velocities will be up. So for our object here, it starts off 64 feet per second. 1 second later, it will have lost 32 feet per second. So after 1 second, its velocity will be 32 feet per second. Because of reasons we don't want to get into, we only need half of that when we're looking at the height function. So here's how the height function will work. We could say, what is the height of the object 1 second after being thrown? So here, if we want to know the height of the object 1 second after it's being thrown, we're just going to say x is equal to 1 and plug that into the function. So this just means this 1 second is telling us that x equals 1. So I'm just going to calculate f of 1. So negative 16 times 1 squared plus 64 times 1 plus 80. And we'll just use our calculating machine to calculate this value. Negative 16 times 1 squared plus 64 times 1 plus 80, 128. If I want to know the height of the object, let's say 5 seconds after being thrown, oh, I said 5. We're going to go with 4 now. So if I want to know the height of the object 4 seconds later, we can see what's going to happen. We're just going to say x is equal to 4 in this case. Four seconds, so x equals 4. And we do the same thing. We just plug it into the function. So f of 4 will be negative 16 times 4 squared plus 64 times 4 plus 80. So let's find out. I'm going to do the same calculation. I'm just going to replace my 1 with 4. So 4 seconds after being thrown, it's come down. It starts off at 80. It went at 1 second later, it's up at 128. And then 4 seconds later, it's back to the same height it started. So if we were standing on a tower and we threw this object up, 4 seconds later, it would go past in front of us. So it's at 80 feet per second, or sorry, 80 feet. Let's think about what should happen to this function. At 0 seconds, it was 80 feet and going up. 4 seconds later, it was 80 feet and going down. Let's draw a picture of what needs to happen in this function. So we know that the object will start by going up and then reach some maximum height and then start falling. So we know some things already. This is a quadratic function, so its graph is going to be a parabola. It's got a negative leading coefficient, so the parabola is going to open up down. And that makes sense because we should see a parabola that goes up. We should see things going up, reaching some height, and then coming down. So here's what a little bit wobbly on my parabolas. So one thing that we get from the standard form is that when f is 0, y is 80. So f of 0 is 80. That's one of the great things, the easy things we get from the standard form. I don't know if it's a great thing. It's one of the easy things to find from the standard form, the y-intercept. So we can see that the y-intercept So I'm going to decide that this is where the y-axis should be. And so this point is going to be 0, 80. 0 seconds after the object was thrown, its height was 80 feet. And that's how we would interpret that y-intercept. Since we're looking at a parabola, we know that we are going to be concerned with finding the vertex. The vertex is where we reach maximum height. There's an x-intercept. Well, there's two x-intercepts. One happened before 0, so this was before the object was thrown. But this second x-intercept, the positive one, this is when the object must have landed on the ground. So here are some points that we'll be interested in about this parabola: the x-intercepts, the vertex, the y-intercept, and any other points that we happen to come across. This other x-intercept happens before the object was thrown, but we're going to be interested in that one anyway. So that's time t minus 1, because it's 1 second before the object was thrown. So that was kind of happening in the countdown phase. Probably the object was not on the ground at that point. We were standing up here on this 80-foot tower getting ready to throw the object up. All right. We want to find some things out about what's going on. We know that the initial upward velocity was 64. We know that 1 second later, the object was at a height of 128. That's something that we calculated in the previous, just doing a previous example. One of the points here is 1 and 128. Another piece of information that we had found is 480. 4 seconds after being thrown, the object was at height of 80 feet. Let's go about and find some other information. We have the standard form, negative 16x squared plus 64x plus 80. We know that one of the things that we want to know is the vertex. And we know how to go from standard form to vertex form. So we have f of x is negative 16x squared plus 64x plus 80. This is our standard form. And let's switch this over to vertex form. We know that the leading coefficient doesn't change in form, so it's going to be negative 16 times x minus something squared. And it looks like the vertex is going to have a positive y-coordinate. So let's find the vertex. The vertex is negative b. The x-coordinate of the vertex is the opposite of b over 2a. So h is negative b over 2a. And so that in this case is negative b, which is 64, divided by 2 times a, which is negative 16. So that's going to be negative 64 over negative 32, or 2 seconds. Because h is an x-coordinate, and x's are in seconds. Before we go on, we should also notice that we have 2 points with the same y value, 080 and 480. And so the vertex should be halfway between any 2 points with the same y-coordinate. So if these 2 points, 080 and 480, are on the parabola, then halfway between should be where the vertex is. So we should make a note of that. Note, the vertex is halfway between 2 points with the same y-coordinates. The vertex should always be halfway between any 2 points with the same y-coordinate because of symmetry. If we want the y-coordinate of the vertex, I need to plug the 2 seconds into the function. So let's do that. So k is going to be the function evaluated at h. So it's going to be negative 16 times 2 squared plus 64 times 2 plus 80. And I'll just use a calculating machine for that. Plug in a 2, plug in a 2. So it looks like the maximum height is going to be 144, and this will be in feet. So it looks like the vertex is negative 16 times x minus 2 all squared plus 144. There's the vertex of 2, 144. The vertex is the maximum height. So the maximum height of the object is 144 feet, which occurs 2 seconds after being thrown. That's how we would interpret the vertex at 2 and 144. Let's take a look at this graph. Let's take a look at this graph on a graphing calculator. So here I've got the graph of y equals negative 16x squared plus 64x plus 80. And we can see here we have that point 0, 80. And we've got the vertex at 2, 144. So if I look at the graph of negative 16 times x minus 2 squared plus 144, we get the same graph. Our y-intercept is 80. Our x-intercept is at 2, 144. Here's another point at 480. If I draw the graph of y equals 80, then we can see that intersection there. 0, 80, and 480. And then there's our vertex halfway between. Another question that we might have is, when does the object land on the ground? So we know from just from the picture we drew earlier, the x-intercept should determine where the object lands on the ground. So if we find the x-intercept, we see we have an x-intercept at 5, 0, and the other x-intercept is at negative 1, 0. The negative 1 doesn't count. That was 1 second before the object was thrown into the air, but 5, 0 indicates that 5 seconds after being thrown, the object landed on the ground. So let's include that in things that we have noticed. So this x-intercept is at 5, 0 from Desmos. Just by looking at our graphing calculator, the object lands on the ground 5 seconds after being thrown. And that's how we would interpret that point. We could say 5 seconds after being thrown, the object lands on the ground. which is another way to say height is 0 feet. We can interpret this point in the same way we do all the points. 5 seconds after being thrown, the height of the object is 0 feet. But in the context, it makes more sense to say the object lands on the ground. That's how we interpret the point 480. 4 seconds after being thrown, the height of the object is 80 feet. That's how we interpret the vertex. 2 seconds after being thrown, the height of the object is 144 feet. But for the vertex, we want to include the extra information that this is the maximum height of the object. So 2 seconds after being thrown, the object reaches its maximum height of 144 feet. And we got at that vertex either because we knew 2 points with the same y-coordinate, we just split the difference, 0 and halfway between 0 and 4 is 2, or we could use h equals the opposite of b over 2a, and then plug h into the function for k. The other form of a quadratic function that we are going to be interested in, the one that I said I would introduce today, has to do with the x-intercepts. So when we look at this function, we have x-intercepts at -1 and 5. So what I want to do is introduce this form. I still want the leading coefficient to be -16. These are points when -1 and 5 are points where the function is equal to 0. So if I plug in 5, I should get 0. If I plug in -1, I should get 0. So if I build a factor that says x plus 1, then when I plug -1 into this factor, -1 plus 1 is 0, and anything else that's going on in this function doesn't matter, because we're going to get a value of 0. Similarly, if I plug in a 5 into x minus 5, I get 0. And so now I have the same leading coefficient of -16, and I have this factored form, which is telling us the x-intercepts. So with x-intercepts at -1 and 5, that means x plus 1 and x minus 5 must be factors of my polynomial. And these are unaffected by the leading coefficients. So let's summarize that. The x-intercepts of -1, 0 and 5, 0 tell us that x plus 1 and x minus 5 are factors of f of x. That is, we can write f of x as -16 times x plus 1 times x minus 5. And this is the factored form. If I multiply out x plus 1 times x minus 5, I should verify that this is actually the same function. But if I multiply out x plus 1 times x minus 5, I get x squared minus 5x plus x minus 5. And all this is going to get multiplied by -16. So I got x squared minus 4x minus 5 times a -16, which is -16x squared plus 64x plus 80. To go from factored form to standard form, we just need to multiply. This is the same way we go from vertex form to standard form. We just multiply out x minus 2 squared. multiply that by the result by negative 16, and then add 144. Just looking at that expression and following the order of operations. Exponents go before multiplication. Multiplication goes before addition. We're just following the order of operations. In the factored form, to get the standard form, we're just doing multiplication. It's three things that are being multiplied together. I can multiply them in whatever order I want. I could have multiplied negative 16 times x plus 1 and then taken the result and multiplied by x minus 5. 2 times 3 times 5 can be 2 times 3, which is 6, times 5, or 30. Or it could be 2 times 5, which is 10, times 3, which is 30. Or 3 times 5, which is 15, times 2, which is 30. All we have is a bunch of multiplication. We just do whatever order is convenient for us. So there are the three forms of a quadratic function: the standard form, the vertex form, and the factored form. Each one of them has some kind of information about the graph. The standard form, it's really easy to pick out the y-intercept because it's really easy to plug in 0. The vertex form has the vertex right in the form. That's why we call it the vertex form. And the factored form is going to tell us what the x-intercepts need to be. So each form tells us a different piece of information. And that means if we have one of them, we have all the others. All right, that's what I wanted to talk about today, the three forms of a quadratic function. I want to look at this a little bit more tomorrow, but for today, that will do it. Everybody have a good day, and thanks for playing.